Hi, this is our presentation on task agnostic continual learning via math learning. This is a joint work with Jakub, Alexander, Andrei, EY, and Razvan at DeepMind. This work was done during my internship at DeepMind. In continual learning, the goal is to learn a sequence of tasks without forgetting. We notice that many works in continual learning literature actually make two underlying assumptions. The first is that task information, including task labels or the boundaries between different tasks, is always available. The second is that there always exists a multi-task solution that solves all the tasks so far. While these two assumptions might be valid in a task-aware scenario, they do not hold in a task-agnostic scenario where task information is unknown and the right solution depends on the task, which is hidden. Examples of such scenario include multi-agent games. In such games, the task for one agent depends on the configurations of the other agents, which are hidden from this agent. And the other agents are also learning, so the tasks are changing all the time. There's no clearly defined boundaries between different tasks. Even worse, different tasks might conflict with each other, so the optimal solution for task A might be detrimental for task B. Perhaps the most well-known example in machine learning is GAN. From this equation, we can see that the optimal discriminator depends on the generator distribution. So this means that the same discriminator cannot be optimal for two different generators. Suppose one generator at the beginning generates mode A in this picture, and later shift to mode B. And if the discriminator is trained to be optimal for a generator with respect to mode B, it can no longer be optimal for the generator that generates mode A. And this means that the generator can simply fool the discriminator by going back to the mode that it used to generate. And this will cause the training process to enter a mode revisiting loop, and it will never converge. In order to address these problems, in this work we propose a framework called the what and how framework. To address the problem that task information is unknown, we propose to explicitly infer the task representation from context. This answers the question what task it is. And since the right solution depends on the task, which is hidden, we ask our model to depend on the task representation, and this corresponds to the question how to solve the task. There are two components in this framework. The first component is a word encoder, which maps the context data dctx to the task representation ct. And the second part is a how decoder that decodes the task representation ct to a task-specific model ft. In this work, we simply choose the previous k observations as the context data. This choice is reasonable in a scenario where tasks change very smoothly or it is piecewise constant. In order to implement the framework, we notice that many math learning methods are actually task inference methods, and they also have a word encoder and a how decoder. For example, Mammal use one step or a few steps of gradient descent as the word encoder that maps the context data to a task-specific parameters, and the how decoder is simply reparameterizing the model by the task-specific parameters. In order to learn the metaparameters online, we apply online variational Bayes on the metaparameters. The posterior of the metaparameter can be recursively updated by this Bayes rule, and at each time step t, we approximate the real posterior by a parametric distribution qt by minimizing the KL divergence between q and the real posterior. The likelihood term can be simply approximated by the what and how framework result given the correct context data, and the prior term can be approximated simply by the previous parametric distribution qt minus 1. If we choose a diagonal Gaussian distribution as the posterior, then we can obtain a closed-formed update rule for the mean and variance of the Gaussian. And here we can see that the update rule for the mean can use the variance as the learning rate. The intuition behind this is that the more certain we are about the parameter, the less we want to change it in the future. Here is the final algorithm we used for the what and how framework using Reptile, which is a meta-learning method that can be considered as a first-order approximation of Mammal. We choose it because it's more efficient as it does not require backpropagation through the inner loop process. In order to evaluate our framework, we designed several experiments, including an experiment called label Permuted MNIST, and more classical experiments such as Permuted and split MNIST. Details of these experiments can be found in our paper. Here I will mainly focus on the experiment based on GAN. We notice that the objective function of GAN is a minimax function, which can be rewritten as simply minimizing a loss function with respect to the generator parameters theta g. This is possible if we have a function theta d star that returns the optimal discriminator parameters given the generator parameters. In practice, we do not have this function, so people usually approximate it by one step of gradient descent from the current discriminator parameter. However, as we discussed before, the discriminator parameters cannot be optimal for two different generator parameters, so this means that theta d star has no memory of previous generators. In order to resolve this problem, we can apply the what and how framework, and we approximate the function theta d star by the word encoder that maps a min batch of data generated by the generator to the optimal discriminator parameters. Now, since for different generator parameters theta g and theta g prime, the word encoder can simply map to different optimal discriminator parameters conditional on the data generated by the generator. So in theory, one set of metaparameters can be optimal for multiple generators, and this means that the theta t can remember all previous generators. To test if this method can prevent the training process from entering a mode revisiting loop, we first applied it to a simple 2D mixture of Gaussian dataset. We trained a vanilla GAN and a GAN using the what and how framework. As we can see that the vanilla GAN will actually enter a mode revisiting loop, and the training process did not converge even after 10,000 steps. However, for the what and how GAN, although at the beginning there's also a mode collapse problem, but it did not enter a mode revisiting loop, and in the end the distribution converged to the real target distribution. We also applied this method to train a deep convolutional GAN on CIFAR 10 dataset. Here we cannot directly visualize the mode collapse problem, so we choose to measure this problem by two metrics called NDB and GSD. The lower these metrics are, the less mode collapse is happening. And as we can see here, the what and how GAN has significantly lower NDB and GSD while maintaining the same level of FID and IIs, which measure the qualities of the images generated. To summarize, we propose a framework called the what and how framework in this work, and there are two ways of viewing this framework. From the continual learning perspective, the what and how framework addresses the task agnostic continual learning problem by explicitly inferring the task when the task information is not available and the multitask solution does not exist. From the math learning perspective, the what and how framework addresses the continual math learning problem by applying continual learning techniques on the math level, therefore allowing math knowledge to accumulate over time. With this, I come to an end, and thank you all for your attention and time.